Hey everyone, welcome back to Chem Story. Today we're diving into one of the important intermediates in organic chemistry, carbocation. These guys show up all the time in reaction mechanisms, so if you really want to understand how organic reactions work, you've got to get comfortable with how carbocations behave. We'll talk about what they are, what makes them stable or unstable, and how that stability affects the kinds of reactions they take part in. So, let's break it down step by step and get a clear picture of how carbocations really work. So, what exactly is a carbocation? It's an intermediate where a carbon atom has a formal positive charge. Now, normally carbon likes to form 4 bonds. That's how it fills its octet. But in a carbocation, it's only bonded to 3 other atoms. That means it's left with just 6 valence electrons, 2 short of a full octet, and that makes it seriously electron deficient. Because of this, carbocations are super reactive, especially toward anything that can donate electrons. In fact, they're strong electrophiles. They're basically on the hunt for electrons, which is why they're often attacked by nucleophiles, or species that are rich in electron density. Before we dive into the actual structures, let's quickly go over how carbocations are classified. There are 2 main ways to classify them. One is by hybridization, and the other is by how many substituents are attached to the positively charged carbon. Alkyl and vinyl carbocations differ in hybridization, and that directly affects their stability. Also, carbocations can be classified as methyl, primary, secondary, or tertiary, depending on how many alkyl groups are attached. Now, let's take a closer look at the actual structures, so we can really see what's going on. In the first diagram, we've got a lineup of alkyl carbocations from tertiary all the way down to methyl. These are the most common types you'll run into, and they all have one key feature in common. They're sp2 hybridized, which gives them a trigonal planar shape, and they have an empty p orbital sticking straight up. That vacant orbital is what makes carbocations so reactive. They're just waiting for something to come along and donate electrons. Now, take a look at how the number of alkyl groups changes across these structures, from 3 in the tertiary carbocation all the way down to none in the methyl carbocation. You might already be guessing that this affects how they behave. We'll talk about exactly why that matters for stability a bit later on. Let's move on to another important type, vinyl carbocations. In the diagram, we're looking at 2 examples, a primary and a secondary vinyl carbocation. Now, here's what makes these different. The carbon with the positive charge is directly attached to a double bond, and unlike alkyl carbocations, this carbon is sp hybridized. That means its geometry and electron distribution are a bit different, and that has a big effect on how it behaves in reactions. We'll take a closer look at what that means for reactivity and stability in just a bit, when we dive into the key factors that affect carbocation stability. So, what actually determines how stable a carbocation is? It really comes down to electron density and how well that positive charge can be spread out. Remember, when a carbocation forms, the carbon is missing 2 electrons. It's super electron deficient. But there are a few ways the molecule can stabilize that situation, and that's what we're going to focus on now. There are 3 main effects that help carbocations stay more stable. The first one is called sigma donation, or more commonly, the inductive effect. This happens when surrounding groups, like alkyl chains, push some electron density toward the carbocation. Alkyl groups aren't super strong donors, but they are enough to make a difference. So the more alkyl groups you have around the carbocation, the more they help share the load. That's why tertiary carbocations, with 3 alkyl groups, are more stable than secondary or primary ones. Now, the second effect is called pi donation, also known as the mesomeric effect. This one involves lone pairs or pi bonds from a neighboring atom or group. If those electrons can interact with the empty p orbital of the carbocation, they can delocalize the positive charge. That means the charge gets spread out over multiple atoms, and that kind of resonance makes the carbocation much more stable. Another major factor that helps stabilize carbocations is something called hyperconjugation. It might sound a little technical, but the idea is actually pretty simple. Hyperconjugation happens when a CH sigma bond from a neighboring carbon overlaps slightly with the empty p orbital of the carbocation. This overlap lets some electron density spill over into that empty space, helping to spread out the positive charge a bit. The more of these interactions you have, the more stable the carbocation ion becomes, and that's another reason why tertiary carbocation ions are the most stable. They've got more adjacent alkyl groups, and that means more CH bonds nearby, leading to more hyperconjugation. So it's not just about inductive effects or resonance. Hyperconjugation adds another layer of stabilization that really matters. Resonance stabilization is another powerful way carbocation ions can become more stable, and in some cases, it makes a huge difference. When the positive charge can be spread out over multiple atoms through resonance, the carbocation ion becomes a lot less reactive and much more stable. You're not just dumping all that positive charge on one carbon, you're letting the entire system help carry the load. This kind of stabilization shows up clearly in things like benzyl and allyl carbocation ions. In the benzyl carbocation ion, for example, the positive charge isn't stuck on that one carbon. It actually delocalizes into the benzene ring. That resonance across the aromatic system makes the whole structure much more stable. The same kind of resonance happens in the allyl carbocation ion too. Here, the positive charge is delocalized across 3 adjacent carbons in a conjugated system. Instead of being stuck on one carbon, the charge is shared, and that makes a big difference. Thanks to this delocalization, the allyl carbocation ion is way more stable than a regular primary carbocation ion. Now, if allyl carbocation ions are so stable thanks to resonance, you might be wondering, what about vinyl carbocation ions? The positively charged carbon is part of a carbon-carbon double bond, right? So you might expect some kind of resonance stabilization. But, surprisingly, they're much less stable. Let's break down why that is. First, the orbitals don't line up the right way. The empty p orbital on the positively charged carbon is perpendicular to the pi system, so the charge can't delocalize, and no resonance means no extra stability. Second, the hybridization makes things worse. The carbocation ion carbon is sp hybridized, which means it has 50% s character, and that pulls electrons closer to the nucleus, making it even harder to spread out that positive charge. So with no resonance, and a very electron-tight hybrid orbital, vinyl carbocation ions end up being way less stable than alkyl, allyl, or benzyl carbocation ions. That's why they're rarely seen, and only form under really harsh conditions. Alright, now let's talk about some common reactions where carbocation ions actually show up. You'll see these intermediates pop up all the time, and they have a big impact on both how fast the reaction happens and what kind of product you get in the end. One classic example is the addition of hydrogen halides, like HX, to alkenes. Here's how it works. First, the alkene reacts with a proton, and that creates a carbocation ion intermediate. Then, the halide ion, like Cl- or Br-, comes in and attacks that positively charged carbon. And just like that, you get your final product. So the formation and stability of the carbocation ion directly affect the path and speed of the reaction. The SN1 reaction of alkyl halides is a great example where carbocation ions take center stage. Here's how it works. The leaving group drops off first, and that creates a carbocation ion. Only after that does a nucleophile come in and attack. And here's the key point. The rate of the reaction depends entirely on how stable that carbocation ion is. The more stable it is, the faster the reaction goes. There's also a similar process called the E1 reaction, where a carbocation ion forms the same way. But instead of being attacked by a nucleophile, a base removes a proton and elimination happens. But in both cases, the carbocation ion is the key step, and that's why understanding how they form and how stable they are is so important for mastering reaction mechanisms. Carbocations also play a big role when it comes to the reactivity of alcohols. Under acidic conditions, alcohols can go through either substitution or elimination, and both of these often involve a carbocation ion intermediate. Here's what happens. The alcohol gets protonated first, turning that OH group into a better leaving group, water. Once water leaves, you're left with a carbocation ion. From there, the reaction can go in 2 directions. Either a nucleophile attacks to give you SN1, or a base pulls off a proton, leading to E1 elimination and the formation of an alkene. So yeah, even something as simple as an alcohol can react through a carbocation ion, as long as the conditions are right. Even in electrophilic aromatic substitution, or EAS, carbocations play a role. When a benzene ring reacts with an electrophile, it briefly forms a carbocation intermediate. This breaks aromaticity for a moment. But the positive charge is stabilized by resonance across the ring. That resonance makes the intermediate stable enough to exist, just long enough for the reaction to finish. After that, a proton is lost, aromaticity is restored, and the substitution is complete. And that intermediate, it actually helps decide where the electrophile ends up. That's regioselectivity. So even though benzene is super stable, it still depends on carbocation chemistry to react. Another important reaction that involves carbocations is the acid-catalyzed cleavage of ethers. When ethers react with strong acids like HBr or HI, the oxygen gets protonated. If the carbon next to that oxygen is tertiary, the leaving group can break off, forming a carbocation. Once that happens, the system becomes highly reactive, and a nucleophile like Br- or I- can attack. This breaks the bond, usually giving you an alcohol and an alkyl halide, depending on the conditions. So even in ether cleavage, carbocation stability matters, especially under acidic conditions. At the end of the day, understanding carbocations is key to predicting reaction mechanisms and designing better organic transformations. All right, that wraps up today's lesson. Thanks for watching, and if you found this helpful, don't forget to like and subscribe. I'll see you next time.